graph algorithms. It's a fair bit of what we are going to talk about should be material that you already know, but we will review some of it so that you can sort of get up to speed and current with your knowledge of graphs and how to apply techniques like depth first search and breadth first search and so on. So presumably we all know what graphs are. So graphs have vertices and edges, right? And there are a number of problems that we are interested in can be modeled in terms of graphs. Okay. So formally, a graph consists of a pair of sets V and E. V is the set of vertices. E is the set of edges, right? And an edge is denoted as a pair of vertices, and it basically says that there's a if you say U comma V, that means there is an edge starting from the vertex U to vertex V. Okay, so that's U comma V, or V1 comma V2 means there's an edge from V1 to V2. Okay, there is also the notion of a subgraph. Okay, so a subgraph means the set V prime, the set of vertices in a subgraph should be a subset of the set of vertices in the original graph, and but then E prime is not an arbitrary set, but in fact it includes all the edges between the vertices in the original graph. Okay, so there are two basic ways to represent graphs. One is called the adjacency matrix, and the other one is an adjacency list. Right? An adjacency matrix is a matrix. So if you have n vertices, then you have a matrix with n square elements, right? So it's basically an array representation where you have an array A, and it says so Aij equals 1 if there is an edge from vertex I to vertex j, right? So that's the definition of a adjacency matrix. And the adjacency list, instead of using an array, you use more like a linked list, right? So what you're going to do is associated with each vertex, you are going to keep all of the edges that are incident on that vertex. Right? So if you have your vertex V, then every edge of the form V comma U, right? So these are edges that are starting at V. All of these edges are kept together with the vertex V, and this is called an adjacency list. Okay? So adjacency matrix uses n square storage because it's basically a two-dimensional array, right? Where each dimension is of size n. Therefore, an adjacency matrix requires n square storage, but adjacency list requires only as much storage as the number of edges, right? Or strictly speaking, it requires as much storage as the sum of the number of vertices and the number of edges, right? So in practice, you think the number of edges will be more than the number of vertices in your graph. So many times we would just say O of E because we have this implicit assumption that the number of edges is larger than the number of vertices, right? If not, then we have a graph. Let's say if V is much larger than E, what can we say about the graph?
Sparse.
It's very sparse, right? So basically, what that means is that most vertices have no edges connected to them, right? So it's not about sparseness; it's about the fact that the graph is there is hardly any connection in the graph because most vertices are are by themselves with no edges on them. So that's why it's not that interesting to have graphs where the number of vertices is much larger than the number of edges. Okay. Any questions, right? So this is all very straightforward things that you already know, right? Anybody here who hasn't heard whatever I said so far? Okay, so I guess if I ask the question the other way, then there will be more hands going up. Okay, so depth first search. So we all know what depth first search is, but let's define it in a let's specify, let's describe a specific algorithm for doing DFS, because that allows us to formalize certain properties associated with depth first search. Okay, so so this is the DFS algorithm. So it's a recursive algorithm. What it does is, so it goes through every vertex in the set of vertices in the graph, and then it initializes them so that you know that you haven't seen them yet. And then you pick the vertices one by one, and if they are not already visited, then you call this function called explore, right? And explore is going to first say that it has visited this vertex, right? So explore, so you want to explore this graph, v comma e, starting with the vertex lowercase v, right? So, so this is the root of what you're going to explore, and so you first said, okay, I have visited this root. But if you have already visited it even before getting here, then you won't call explore, right? So that's the idea. And now let's look at this these two lines. So we are going to call a function called previsit before visiting the children of v. And after visiting the children of v, then we'll call post visit. Okay, so it's just a way to say that. See, again, a depth first search is not done just because you want to do depth first search, right? So you do depth first search because you are trying to solve some other problem, right? So in the context of that some other problem, you might be interested in taking some actions during the depth first search. So this is the action that you're going to take during depth first search before visiting the children of this node, and this is a set of actions that you're going to take after visiting the children. Okay. So for now, what we will do is, okay, so it's just an interesting point about how a maze exploration problem could be understood in terms of a graph and the fact that a depth first search of the graph essentially amounts to an exploration and mapping of the maze, right? So in the maze, basically every in a sense every so here is the partition A and then partition C and so on, and then there are connections between them, and so there is a way to go from A to D and then A to C and so on, and so those are captured here, right? And similarly you can go from A to B and so on. So, but let's just look at what a depth first traversal would produce. So when we use a depth first traversal on a graph, we construct what we call as a DFS tree. Okay? So what is a DFS tree? In particular, if you go back to the algorithm, right? So so when our we are going to visit a child of a vertex, right, during DFS, right? So we do that visit only if that child has not been visited before, right? So anytime we go forward and visit the children, we are going to call that as a tree edge, right? So for instance, let's look at this example. Let's say that we start a DFS search at vertex A, right? So from vertex A, let's say you first visit vertex B, okay? So now, if you are at A, you check whether B has been visited. B has not been visited, right? So you're going to go visit B, okay? So because B has not been visited, this is going to become a tree edge, okay? And from B, then you're going to look at its neighbors, and in this case, you're looking at E and then F. So you have E, right? So, so you visit E, and once again, since E has not been visited before, this is going to be a tree edge, right? And then from here, E, you're going to visit I. This is a tree edge, once again, because I has not been visited. From I, you go to J, and J has not been visited, right? So all of these are tree edges. But when you call DFS on J, it's going to find that it has a connection to E, right? So when it has a connection to E, then what happens is that E has already been visited, so this is not going to be a tree edge, okay? So we call this edge a back edge because it goes from a child to an ancestor in the DFS tree, okay? So then all of these recursion unwinds, you come back to B and then visit the next child of B, which happens to be F. And once again, by this time, F has not been explored, so F is going to be, this is going to be a tree edge, and then you go to C, and then from C, the neighbor is A, which has already been visited, right? So therefore, this is not going to be a tree edge, and so on, okay? And ultimately, the traversal ends, okay? So, so you can easily see that DFS uses something like O of E plus V time, right? So because every edge has to be checked, right? And therefore, the total time spent will be order of E plus V. Okay? Any questions? Again, so far, not much new, except that we define the notion of a tree edge and a back edge. Okay? And we'll come back to those later on. So what we are going to do now is we are going to So we can use DFS to find connected components of a graph, right? So connected components means, so far we have been considering undirected graphs, right? So the edges are not directed. So if you draw an undirected edge, that means you can go from E to J or J to E, right? So far we are talking about graph where the edges have no direction, or you can think of them as bidirectional, right? So either way, in those graphs, you can define a connected component, which is a maximal subgraph where there is a path between any two vertices in that subgraph. Okay, so you can start from any place in that subgraph and reach any other node that you want to get to. Okay, so you can imagine, at least it should be intuitively obvious that when you do DFS, starting at one of the nodes in a connected component, you'll go and visit every other vertex in that connected component, right? So, so again, if you go back to the DFS algorithm here, right? So when we call this explore, right? Explore is going to end up finding a connected component because it keeps going forward until it can do that no more, right? And when explore returns, at that point it has found a connected component. Okay. Okay, so we are going to associate some numbers during the DFS. Okay, so we said earlier on we will take some actions before going in and after calling explore. So right now let's just define this action as simply adding a number to the node, right? So we have so we are going to keep a global counter, which for whatever reason is called clock. And so what you do is in a pre-visit, you take the current global counter value and assign that as the pre-number of a vertex, right? Pre means before you start visiting the children of that vertex, right? So or rather, the first time you come to that vertex, you're going to give a number that's called the pre-number, okay? Similarly, you're going to do the same thing when you complete, right? So post-visit is done after finishing the exploration of all the children, and at that point, you're going to assign a number that's called a post number, okay? So now, once you assign these numbers, and once again, notice that this is just a global counter, so every time you assign a number, then you just increment that global counter so that these numbers are given successively, right? So, so now, given these number, then we can make this observation. Given two vertices u and v, the intervals pre-u and post-u and pre-v, post-v are either disjoint or one is contained entirely within the other. Okay, so let's try to understand that. So let's say you are at some vertex v, okay? And then let's say somewhere down during DFS, you come to a vertex u, okay? So you know that if these are all, again, assume that these are all three edges, okay? So then the explore of u, right, will start after explore of v, and it will end before explore of v, right? So basically in a depth first search, you have the last in first out property, right? So the ones that are further down are you are going to start on them later and finish on them before the parents, right? Which means that if I have a pre of v and pre of u, because we started this exploration after this, right? Pre of u should be greater than pre of v, right? Similarly, if you look at post of u and post number of v, once again, this should be finished before you get here. Therefore, post of v should be greater than post of u, right? So what this says is that this interval pre-v, post-v will strictly, or rather, this will be a subset of that, right? So this is going to represent a subinterval of that interval pre-v to post-v, right? So this is the case when you have u being a descendant of v in the depth first tree, right? If u and v happen to be unrelated, right? So let's say you consider another example where there is a w and u is here and v is here, right? So then what's going to happen is that pre-U, post-U, right? So we can easily see that post-U, because you'll finish traversing U and then go back up to W, and then only you're going to come to V, which means that post of U should be less than pre of V, right? Which means that these two intervals are completely disjoint. Okay, so that's all we are saying, right? So these are the only two cases, right? Either it's a descendant or it's not a descendant, right? And we made an assumption here that, okay, they have a common ancestor for this explanation, but that's not, strictly speaking, not required. But so even if there is no ancestor, somehow then you will finish this whole connected component and then come to this connected component, right? And once again, you can easily say that, you know, this traversal is finished before you come here. So once again, these intervals do not overlap. Okay, so so let's again so go back to this picture. So so this is a DFS of right. So this is a DFS of this graph, right? And in addition, you have the pre and post numbers attached to each of the nodes, right? So you start at A, therefore its pre number is going to be 1, and then from there you visit B, right? So its pre number is going to be 2. It doesn't have any children, so you are immediately done. So it gets a post number of 3. Then you go back, come here, pre number 4. You go to I, pre number 5, J, pre number 6. And then it doesn't have any unvisited children, so you come back, so therefore it becomes, its post number is 7, and then you return to I doesn't have any other children, so its post number, its exploration is finished, you assign the post number 8, and then you come back to E, and once again E doesn't have any more children, and therefore you assign the post number, the current clock value, which will be 9 at this point, and you again now this whole connected component is done. Then you're going to look for the next vertex that still remains unvisited, and let's say you find C as the next unexplored vertex, then you're going to assign its pre-number. And I'm sorry, I missed the fact that you're assigning post number of 10 to A, and after that when you come here, therefore the pre-number is going to be 11. Okay, and so on. So, so this is so far, we were considering graphs where the edges were not directed. Okay, so let's look at what happens when you have a directed graph, meaning that the edges have a direction. So in this case, for instance, you can go from A to B, but there's no edge for going back from B to A. Okay? So in the case of directed graph, let's say you start at A, and then you visit its child B. So that's, once again, that's called a tree edge, because you are going to, you're seeing a vertex B which has not been explored yet. And from B, it has its child E, and E has 2 edges, in fact 3 edges. You visit F, and then you visit H, right? And because from F, you would have already visited G. When you go to H, you know, you're not going to take the path, right? So E has a tree edge to F, F has a tree edge to G, right? But H does not have a tree edge to G, because by the time you get to H, your F is already, your G has already been visited, right? So, so once again, the pre and post numbers are shown. So that's not that's the same thing as before. Okay. So now for a directed graph, we have three types of edges. You have a tree edge, which is shown solid, a back edge, which which goes in this way. You could also have a forward edge in an undirected graph, right? Let's see if we can find a forward edge in the example. Do we have a forward edge? I guess we have a forward edge here, right? From E to G is a forward edge in a directed graph. And let's see whether we have that. In the undirected graph, right? Obviously, there is no forward and backward because there is no direction. So we in the undirected graph, we'll call everything as a back edge, right? Okay. So, but in a directed graph, you can have a new type of edge called a cross edge, okay, which goes from which connects two nodes that have no ancestor-descendant relationship. Right? So you can see that you have H to G, right? So this is a cross edge, and that is a cross edge. Okay. So this is a forward edge because E is actually an ancestor of G in this tree, right? In the DFS tree, E is an ancestor of G. So this edge will be called a forward edge. Okay. B is an ancestor of F. Therefore, this will be called as a backward edge. But between H and G, neither is an ancestor of the other. Therefore, it is called a cross edge. Okay? And cross edges have to go from right to left, right? They won't go from left to right. Because if they go from left to right, that means while you were, so for instance, again, let's look at the example. So for instance, you cannot have a cross edge, you cannot have a cross edge from G to H, for instance, because when you get to G, right, the reason why you have drawn H to the right of G is because you came to H after finishing the traversal of G. But if G had an edge to H, then you would not finish the traversal of G until you visit H, right? So therefore, if there was an edge from G to H, that would make H as a descendant of G, right? So the only reason why when you visited G, you couldn't have gone to H is because the edge was directed from H to G. Therefore, you couldn't take it backwards. So that tells you that cross edges have to always go from right to left. Okay? And again, as we said, in the case of undirected graphs, there is no such thing as the direction. Therefore, if there was actually an edge between G and H, then you would visit H from G, right? So therefore, in the case of undirected graphs, you cannot have cross edges. Okay, so in undirected graphs, no cross edges and back and forward edges are the same. Okay, so now we can also make, we already made an observation about the pre and post numbers, but now we can use them to also decide whether an edge is forward, backward, or cross. Okay, so given an edge u comma v, then we can look at the pre and post number. So this left bracket u denotes the pre number, right? And the right bracket u denotes the post number. So what this says is that if the pre-post of v is entirely within pre-post of u, that means v must be a descendant of u. in the DFS tree, and therefore this edge between U and V must be a forward edge. Okay? Similarly, if the situation is flipped, that means, you know, V is the parent and U is the child, so that's, again, then it will be called a back edge. Okay? And then finally, if they are disjoint, that means there is no ancestor-descendant relationship, and in that case, we have said that those edges are called cross edges, right? We define cross edges as the edges that go between vertices that have no ancestor-descendant relationship in the DFS tree. Right? Again, remember all of the things that we're talking about are with respect to the DFS tree. Right? We talk about ancestor-descendant. These may not make sense in general in the context of a graph, but when I say, but here we are talking about first constructing the DFS tree, and then we are talking about ancestor and descendant in the DFS tree. Okay? Any questions? So essentially all we are doing is we are reviewing DFS and summarizing some basic properties of DFS, right? So, we said that DFS can be used to find connected components, but let's try to do something a bit more interesting, right? So, we will define a notion called biconnectivity in undirected graphs. Okay? What is biconnectivity? It basically means that between, you say that a graph is biconnected if there are two distinct paths between any pair of vertices, right? So two edge disjoint paths between any two vertices, right? So if you have that, that means you have two independent paths. That's why we call it biconnected graph. Okay? Connected graph means you must have at least one path between every two vertices. Biconnected means there must be at least two paths between any pair of vertices. Okay? And you can imagine that you might be interested in ensuring biconnectivity of graphs, because if you think of it as, let's say, a network, then it gives you fault tolerance, right? Because if even if some edge is broken, right, that won't really disconnect the graph, because if you disconnect one edge, it can only disrupt one path between any pair of vertices. So there should still be another path that's available, right? So so you might be interested in, given a graph, you might be interested in analyzing it and finding out what is it biconnected, right? Another thing that you might be interested in is, suppose it's not biconnected, then you might be interested in finding out what are these critical nodes, right? Which, if these nodes, something happens to them, right, then the graph can become disconnected, right? So maybe you can make sure that those nodes have some, they are somehow more reliable, or you can decide on how to provide a backup for those sorts of nodes. Okay, so these critical nodes are called articulation points. Okay, so an articulation point is one that lies on every path between vertices V and W. Okay, so what this means is that there aren't two independent paths between V and W. Okay, so because there exists one node that appears in every path between V and W, that means there are two node disjoint or edge disjoint paths between the two. Okay, so no, I'm sorry. I should say, node disjoint paths. Okay, so it's not edge disjoint, but node disjoint. So a bi-connected graph, as we said before, contains no articulation points because there are no critical nodes. Okay, so given a general graph, it may not be bi-connected, but you can break it up into subgraphs, each of which are bi-connected. Okay, so here is an example, right? So there are 1, 2, 3, 4, 5, 6 components in this graph. Okay, so you can see that, for instance, these 4 constitute a bi-connected component because given any pair of vertices, there are 2 node disjoint paths. Okay, so for instance, if you want to go from here to here, you can go that way or you can go this way, right? So that's similarly in here you have 6 nodes in a bi-connected component, and if you want to go from here to here, you have that path or you have this path. Okay, so you can so each bi-connected component is given a single color, right? But the articulation points are the ones that have multiple colors, right? And so what the articulation points denote is, for instance, if you want to go from here to here, you always have to go through this node. Okay, so this is like a choke point, right? If something happens to this node and it fails, then this bi-connected component will be disconnected from everything else. Okay, so that's why we are interested in identifying these bi-connected components. And you can see that some of the articulation points are part of 2 different components, and some of them, like this one, is part of 3 different components, right? Any questions? So what we're going to do now is talk about how one might use a depth-first search to compute bi-connected components. Okay? So again, bi-connected components are not disjoint because the articulation points will lie between, they will connect these bi-connected components. And once again, because we are talking about bi-connectivity, let's assume that the graph is already connected, right? So if disconnected, then we can think about bi-connectivity of each connected component, right? So when you talk about having at least 2 node disjoint paths, to say that there isn't even a single node disjoint path is not that interesting. So we will just confine our discussion of bi-connected components to connected graphs. Okay? So that's why articulation points are going to be connecting these components, because if they are not connecting multiple components, then the whole graph will somehow be disconnected. Okay? So, so the bi-connected components, here is one and here is another. Right? Once again, there is no vertex in between these 2. Right? And that is why the property that that there exists, so the property that there is no shared edge between the paths between these 2 vertices, that is vacuously satisfied because there is no edge, no vertex in between them, right? So that's why this itself will be an independent bi-connected component, and this will be another bi-connected component, and so on. Okay, so bi-connected components are interesting when you have more than 2 vertices involved, because then you have to have a path between 2 vertices that involves at least one other vertex, right? So that's why bi-connectivity is more interesting when you have multiple, more than 2 nodes in a component. Okay. So also, when you have a bi-connectivity, that means there is also a cycle, right? Because if there are 2 node disjoint paths between U and V, that means you can use one of those paths to go from U to V and use the other path to come back from V to U, right? So when you have, say, a graph is bi-connected, that means there is a cycle involving every pair of nodes. Okay? Okay. So now let's see how we might use depth first search to identify articulation points, right? So let's say, suppose I tell you efficiency doesn't matter. Come up with some naive technique for finding articulation points. How would you do that?
We can count the number of edges and the degree at every node. And
so I want you to give me an algorithm when I say naive, right? So the implication is that it can be inefficient, but we shouldn't have to, give a long proof that it is correct, right?
So we just look at the adjacency matrix and count something.
You can do that, but there is, of course, the simplest approach is always you go back to the definition and you apply the definition, right?
Right.
So you take every pair of vertices, you enumerate the paths between them, and check if there are two node disjoint paths between them, right? Unless these two nodes happen to be neighbors of each other, then you can just check that. So that is, obviously that's a horrendously inefficient algorithm, right? So what kind of complexity does it have? If I enumerate every path between two vertices, how many such paths are there in a graph?
N choose n.
So there's an exponential number of paths, right? 2 to the power n type of paths between vertices in a graph, right? That can be up to 2 to the power n. And so, taking the definition and converting it into an algorithm does not give you a very practical algorithm, right? So we are going to start from this exponential or super exponential algorithm, and then instead we are just going to go all the way to the other side where we are going to devise a linear time algorithm using DFS. Okay? So how do we do this? I'm going to give you, once again, try to give you a high-level idea of how to go about finding articulation points. Okay? So let's do this. So we want to find, so our goal is not so much to find bi-connected components, but rather to find articulation points. Okay? Because once articulation points are formed, you can remove them and then somehow or you can break them up and you can find connected components. For instance, a bi-connected component. For instance, let's look at this example, right? So once you find that this is an articulation point, then you know that these are all your bi-connected components. So once you find the articulation point, identifying what are the bi-connected components is not that difficult. Okay? So we are just going to find whether a vertex is an articulation point or not. In order to do this, what we are going to do is we are going to do a DFS. Okay, so we are going to say start from some R, and let's say we come to a vertex VI, okay, and then let's call the set of its descendants in the DFS tree, right? Let's call that the set VI. Okay? So what we are trying to figure out is this, whether this vertex, lowercase vi, is it an articulation point or not. Okay? In order to do this, what we are going to do is, we are going to determine this during a depth first search. Okay? And in order to do that, we are going to call the descendants of vi as the set capital Vi, right? So and then now we can define certain concepts. Now we can talk about VO, right? So Vi is somehow the set of vertices that are inside the DFS tree rooted at Vi, right? And VO is the set of vertices that are outside this DFS tree, okay? And what we are going to say is that, so the idea is that, let's say you have some vertex U here, right? If the only way to get to vertices in VO is by going up to Vi, okay? Then Vi ends up being an articulation point, right? So if there is, think about whether you can go to some vertex in VO, right? If you can go to some vertex in VO without going through Vi, then that means, okay, there is multiple paths, right? Because there's always one path, which is you go up to Vi, to R, to whatever vertex here, right? So there always exists one path, right? And once again, we said we are going to only be interested in connected graphs, so we don't have to worry about whether there exists at least one path between some vertex here and some vertex there. That one path is always there. We are trying to check if there is a second node disjoint path from some place here to an arbitrary vertex here. If it's there, then we'll be able to follow that path. If there is no such path, then the only way to go to that vertex over here will be through here, right? So what we are going to do is we are going to try to somehow keep track of whether, from descendants of Vi, we have a direct path to VO, or do we have to always go through Vi? Okay, this is the high level idea. Now let's go through how. So basically what we are saying is that if there is always a way to go from here to here without going through Vi, right? That means Vi is not a articulation point, because that means anywhere, right? So Vi, because of the way you construct the DFS tree, Vi can be an articulation point only between the nodes here and the nodes there, right? So only to go from here to here, right, you have to go through Vi. If you are already over here, right, you will not have to go through Vi, right? So you have your paths over here. If you want to go across vertices over here, then once again you can, stay right here and you never have to, go through Vi. The reason why you have to go through Vi will be for going from this part of the graph to that part of the graph, okay? And now what we are asking is that, is there an alternate path for going from this part of the graph to that part of the graph without having to go through Vi? Okay? If there is an alternate path for every vertex in the DFS tree rooted at Vi, then we know that there is always a second way to go for each of these vertices into each of those vertices over there, and therefore Vi is not critical, right? Because I could now remove Vi and still I am able to reach anything over here, right? So what we are checking is whether there is this independent path from each vertex here to each vertex over there, right? So observation 1 is basically saying that if there is such a path for every descendant over here to every vertex over here, then this is not a critical node, right? And this is not an articulation point. So let's not worry about the proof. So all we are saying, observation 2 basically says is basically the complement of observation 1. It says that if there isn't a path from, if there exists at least one vertex here, right, that cannot reach some vertex over there, right, that means that the only way you can go from U to that particular vertex is by following this path, which means that VI becomes critical. Right? Therefore, VI will be an articulation point. Okay? So now is when we sort of begin to use the properties of DFS tree and so on. So what we are trying to say here is, well, if you go from here to here, right? So this is not a tree edge, right? Because if it was a tree edge, then this wouldn't be in vivo, right? Because it will somehow be right here under this tree, right? So this must be something other than a tree edge, right? Since we are talking about undirected graph, the only type of edge other than a tree edge is a back edge, right? So this must be a back edge, okay? And being a back edge, it should actually go to some vertex over there, right? It's not that it's going to jump to the side, right? Because we said in the undirected graph, there are no cross edges, there are only back edges, and back edges have to go to an ancestor, okay? The other simplification we are making is, well, it's enough to just consider the immediate children of VI, okay? Because if you talk about, if there is a path from, okay, so the point is that if, let's say, you have a path from some vertex here, right, to some vertex over there, then that means from, at least from one of the children, you would be able to follow that, right? On the other hand, if there exist vertices, right, that cannot go this way, then you can. So again, the question that you're asking is whether there is a way to whether there is a back edge from one of these vertices that takes you back to an ancestor, right? So if every one of those has a back edge going back to an ancestor, then you will be fine, right? So if you have a back edge from one of the descendants over here, then once again you can start from here and somehow reach that vertex, and then you'll be able to follow the back edge. Okay? So what we are saying here is that instead of thinking about every possible vertex here and every possible vertex here, we can confine our attention to just the descendants of VI and the ancestors of VI. Okay? So what that means is that during a DFS, we can ask whether each of these have a path to an ancestor, right? If they do, then VI is not an articulation point. Okay? So this is what we are going to do. We are going, during a DFS, we come to VI, we are going to explore each of these, right? And part of this exploration is going to keep track of what is the ancestor that I can reach from this subtree, okay? And what I'm going to then ask is whether for each of the children of VI, they can reach an ancestor of VI. Okay, if they can, that means there is a way for them to go to all of the nodes without having to go through VI. But if there is even a single child which does not have a way to go back to an ancestor, right? That means that child has only one way to reach the ancestor, which is through the VI, right? And therefore, VI then becomes an articulation point, right? So what we are going to do in the algorithm is we are going to maintain something called low, right? For each vertex V, we are going to maintain something called low of v, which tells us the lowest numbered vertex that can be reachable from v. Okay? So you have a back edge to go to v. And once again, what is the lowest number? Because remember, we are giving DFS numbers to nodes during the DFS traverse. So for instance, this will have a DFS number 1, and this might have 10 and so on, right? So what we are asking is, starting from this vertex, okay, what is the lowest numbered vertex to which we can go using a back edge, okay? And if that happens to be less than 10, right, that means you have a way to go to an ancestor without going through VI. So what we're going to do is we are going to maintain this low number and use that low number to decide whether we need to, whether every one of these children has a way to go back to an ancestor. Okay? And once you've done that, then you're able to decide whether you have an independent path to go from here to the rest of the graph. And if you do, then this is no longer an articulation point. If you don't, then this becomes an articulation point, and then you mark it as such. Okay, so I'm not going to give you more walk through this algorithm in more detail, because it's something that takes to follow it fully requires you to spend quite a bit of time, and I'm not going to spend that kind of time on this particular algorithm. Okay, so let's talk about directed acyclic graphs. Okay, so now we talked about biconnected components in undirected graphs. So now let's come back to directed graphs. Okay, so in directed graphs, what is a DAG? A DAG is a directed graph which has no cycles, right? So during a DFS, you can easily determine whether you are looking at a DAG or not, okay, by checking whether the DAG has a back edge during. If you discover a back edge during DFS, that means, right? So what does that mean? So you are here, right? So there is a U, there is a V. If you discover a back edge, right? So you have a sequence of 3 edges to go from U to V. So the moment you find a back edge, right? Remember, the definition of back edge is going from a descendant to an ancestor in the DFS tree, right? So because this is a descendant of this node, there is a set of 3 edges to go from U to V, and now there is a back edge that takes you from V to U, okay? Therefore, that means there is a cycle in the graph, right? So now, once you have discovered a cycle, it's no longer a DAG, okay? So that's why a directed graph, you can determine whether something is a directed graph, whether something is a DAG or not, by doing a DFS. Okay? So if there are no cycles, then if there are no back edges, then you're going to have only forward edges, right? So forward edges go from lower pre-number to a higher pre-number, right? And cross edges also go from lower, no, it's about post numbers. Okay, so let's write that down. So if you look at the DFS for DFS tree for a DAG, you're going to have 2 types of edges, right? Right, so there is going to be a cross edge and there could be a forward edge, right? So in the case of forward edge, you know that the exploration of this subtree will be finished before you get here. Therefore, let's say we call this u, v, and w, right? So we know that post of v is less than post of u, right? In this case. Similarly, you get to w after finishing with v. Therefore, you know that post v is also less than post w, right? So what we are saying here is that in a DAG, every edge leads to a vertex with a lower post number. So if you look at this edge, it goes from w to v. So we said post w, or our post v is less than post w, right? So the direction of this symbol matches the direction of the arrow, right? So that's what this the second bullet here says, that the direction of this symbol matches the direction of the arrow. Okay, and ultimately, the third bullet says that every DAG has at least one source and one sink, right? So why is that the case? Why must every DAG have at least one source?
One, because there's a root, right? And it's acyclic.
Why must it have at least one source?
It is direct.
Can you give me a simple argument based on the fact that there are no cycles?
There are no cycles, so it must start from something. There must be a node with no incoming input.
It seems so obvious, right? But I feel that it is, sometimes these things are not that obvious, and I feel that there is an even simpler argument that you can make, which is that, let's say, every vertex, right? So let's just look at the sink, right? So let's look, why should every node, every DAG need to have at least one sink?
I mean, we can prove by contradiction. We can say that suppose it has like two sinks, then
It can have two sinks, right? There's no problem. It should have at least one sink.
If it has no sinks, then,
Yeah. Then what would be the problem?
There will be a cycle.
Why?
Because
so we can traverse then such a DAG, and if there is no sink, maybe that means that either it's an infinite sink that we have not reached the end, or if we have reached the end, we are visiting the same node two times.
So in other words, what we're saying is that if every vertex has a way to get out, then you can keep traversing forever, right? Because every time you go to a vertex, there's a way to get out. You go to the next vertex, there's a way to get out. So you can keep going forever, which means that you must be on a cycle, right? Or it is an infinite graph. So generally, we don't worry about infinite graphs. So on a finite graph, if you have, you must have at least one sink. Okay, so that's about directed acyclic graphs. Let's talk about strongly connected components. Okay, so strongly connected components are fairly similar to biconnected components in undirected graphs, but they're also similar to connected components, right? So there is some two distinct notions in undirected graphs: connectivity and biconnectivity. More or less become essentially the same thing in the case of directed graphs. Okay, so why? So because in an undirected graph, if there is a path from u to v, because every edge is bidirectional, you can just reverse it, and therefore there is also a path from V to U. But in the case of a directed graph, the paths become directed, therefore you might be able to get from U to V, but you cannot retrace that path back to V because back to U because the edges are all in the wrong direction, right? So you must have somehow an independent path from V to U, right? So in order to call this graph connected in a directed setting, you have to have a way to go from U to V and V to U, right? So for every pair of vertices in a directed graph, to call that graph connected, you need to be able to go from any vertex U to another vertex V, and then back from that vertex V to U. Okay? So this means that you should have cycles, right? So you must have cycles, and so whenever you have connected graphs, you end up having cycles in the case of directed graph. And also because there are two paths, right? So it looks like you have to have a path from U to V and V to U, so it kind of has become similar to the biconnected, the notion of biconnectivity, although it doesn't exactly match, okay, so but it is quite similar to biconnectivity, but at the same time, to even call it connected, we still need the same property, okay? So, so the definitions are fairly straightforward. So we went through this definition, and then a directed graph is called strongly connected if for every pair you have every pair of vertices you have connectivity. Okay, and you could have a graph which is not strongly connected, in which case you'll be able to split it into pieces such that each piece is a strongly connected component. Okay, so here is an example. Okay, so you have the graph here, and the dotted lines identify strongly connected components. So A here is a component by itself because there's no way to get to A, right? So it's going to be an independent component by itself. Now from B, you can go from B to E, and you can go from E to B. Therefore, these two will be the same connected component, but D is once again an independent component because you cannot go from D to any other place, right? So there is a path from D to anywhere. So therefore, it's going to be an independent component. And you can see that once again, you have two independent components. You can go from B to C and E to F, but there is again no way to come from either of these nodes back to here, right? That's why they are in a separate component. Okay, so this graph has 1, 2, 3, 4, 5 strongly connected components. Okay, and what this is showing is, well, if let's say you collapse each connected component to one supernode, then you will get a graph that's like that, right? This is a graph where each vertex corresponds to one of the strongly connected components. Okay. So let's talk very quickly about breadth-first search, right? So again, I assume that you know what is BFS. So the only thing that I'm going to talk about in BFS, right? So in BFS we are going to use again this visited array so that we don't go back to the same vertex again and again. Secondly, instead of using recursion, a recursive exploration which implicitly uses a stack, we are going to use a queue. And so we are going to dequeue the first element of your queue, and then then what we're going to do is we're going to take each of the descendants or each of the children of u, and we are going to put them at the end of the queue, and then we are going to say that that particular vertex has been visited, right? So once you put a vertex in the BFS queue, then we are going to call it as visited. Okay. So here is an example showing how BFS works. So you start, let's say you start the traversal at S. So you put S into the queue, okay? And now you go into the children of S, and there are, 4 children. So A, C, D, E. So all of them are put into the queue after S is dequeued, right? So you dequeue the first element, and you put all of its children in the queue. Now you take out A, and you queue its child. Therefore, A goes out of the queue, and B goes to the end of the queue, right? And now on, it's kind of not that interesting because there are no more nodes that need to be visited. So your queue, from here on, you just keep popping, removing from the beginning of the queue, but nothing gets added to the queue, and the queue ultimately becomes empty. And so if you draw the corresponding BFS tree, then this is how it looks like. A has A, C, D, and E are the children of S in the BFS tree, and then B has another child in B. So unfortunately, there isn't a lot we can say about properties of BFS graphs. So generally, we don't do much with BFS because it doesn't have many of the interesting properties that we get with BFS. So the only interesting thing about BFS is somehow BFS will automatically compute shortest paths, okay, provided all edges have the same cost, right? So if you say all edges have the same length, now you find the shortest path, then breadth first search can enumerate the shortest paths, right? Because you go by levels, right? So we are talking about how many levels are between a vertex V that you start from and the vertex you want to reach. So if it's going to get there as quickly as possible because of the way it traverses the graph by levels, and so BFS automatically computes shortest paths. But in reality, most of the time we are interested in cases where the edges have different costs, right? So once you have different costs associated with the edges, then BFS does not allow you to compute shortest paths. So you need to be more clever, right? And then use more sophisticated techniques to find shortest paths, and that's something that we will talk about in the next lecture. Okay. So at the very end, I want to talk about an interesting relationship between boolean matrices and paths in graphs. Okay. So earlier on, we said that we are going to, we can represent a graph using an adjacency matrix where Aij equals 1 if there is an edge between I and j, right? And an adjacency matrix can naturally capture directed graphs because you have Aij and Aji, right? So Aij says whether there is an edge from I to j, and then Aji will tell you whether there is an edge from j to I, right? So directed graphs can be captured using these adjacency matrices, and also because the only thing that we are trying to say is whether there is a edge or not, the elements of this array are going to be either 1 or 0, right? So that's why we call it a boolean matrix, right? The elements are all 0 or 1. Now, let's think about, let's say you have a matrix A that represents a graph. Okay? So matrix A that represents a graph, right? So what does A times A represent, right? In particular, let's say B equals A times A, right?